So now that we have looked at the three quantum numbers, N, L, and M sub L, and those are assigned to electrons to tell us where it lives, we're ready to kind of give a place for all the electrons in an atom. And we're going to, after we do that, see what kind of information can that give us about the atom. The electron configuration, how those electrons are laid out in an atom, tell us the properties of that element. So when we get to the end of this section, we are going to be able to know something about the element based upon our understanding of its electron structure. So let us begin here. The first thing I want you to look at and read and be responsible for is the development of the periodic table. What's fascinating to me is that people didn't know anything about the electron structure when they started laying out the periodic table. They started aligning things based upon how they behaved, and they arranged things based upon their chemical and physical properties. And later, as we started understanding the electron configuration, we noticed that that layout has everything to do with the electron structure. So you read about how the periodic table came about. But we're going to look at electron configuration, and we're going to look at it in multiple parts. In this first part, we're going to talk about that spin quantum number. This is the last of the four quantum numbers. We saw the first three in the last unit. Now we're looking at the fourth one, which is a spin quantum number. And we're going to learn something called the Pauli exclusion principle. So let's begin. All right, so what is an electron configuration? An electron configuration, in which we've got multiple parts to this lesson. An electron configuration is just how those electrons are occupying the orbitals within an atom. So we learned what orbitals exist. We learned about orbitals, we learned how they're grouped together in subshells, we learned how those subshells are grouped together into principal shells. Those shells and principal shells and orbitals get occupied by electrons, and so the electron configuration is how those orbitals are occupied. So it shows when we do an electron configuration, we're basically only doing it to the shell and subshell level. We'll tell what the subshell is and how many electrons are in that subshell. By our knowledge about the orbitals and how many orbitals are in each subshell, we can also know where they are in the orbitals themselves. When we do an electron configuration, we will always do it for the ground state. What does that mean? We're going to put electrons in and making sure that the lowest energy orbitals are filled first, and then when that gets filled up, we'll go out to the next higher one and on. And we'll always, when we're asking for an electron configuration, always be asking for the ground state, because you can take electrons and they can be up somewhere up in a higher orbital somewhere, a higher N, a higher S and P value somewhere higher and farther away, and it is an electron configuration, but it's not where they're all ground state, and that it helps us just have a common language across all of the atoms. Okay, so our first one. First example would be the simplest atom. It is hydrogen. Hydrogen only has one electron. And so when we place that electron into its orbital, it's going to be the lowest N, because we know that the smaller the N, the closer it is to the nucleus. And so that's an N equals 1. We know that there's only one subshell in the N equals 1, and we did this last time. We learned that when N is equal to 1, L is equal to 0, and M sub L is from a negative 0 up to positive 0, only that. So this tells me in that first shell, there's an S subshell, and there's only one orbital in there. So that is the closest to the nucleus. That's going to be the lowest energy. And if we're going to put the one electron that hydrogen has into that orbital, that's how we denote it. We denote it with the 1, telling me that N. We denote it with the S, telling me it's in that subshell, and then we do a superscript of a 1 that tells me I have one electron in that subshell. All right, so 1S is the name of the subshell, and that 1 right there tells me I have one electron in that subshell. So the next quantum number we have to deal with is the Pauli, we're going to talk about the Pauli exclusion principle, and we're talking about the spin. So we know that electrons, you didn't know this until now, or maybe you did, but Electrons spin, okay? They have a spin to it. It gives them makes them behave like a little magnet, okay? And they have an option. They can either spin one way or they can spin the other way. And that's it, okay? So there's two directions to their spin. All electrons are going to have the same amount of spin, value-wise, but one will spin in one direction, maybe we'll call it clockwise, and the other one will spin in the other direction, we'll call it counterclockwise, okay? Now, clockwise and counterclockwise means, how are you looking at it? Are you looking at it from the top down, are you looking from the bottom up? I don't know, but once you call one clockwise, the other one is spinning the other direction, we'll call it counterclockwise. So we'll use that language with it, okay? So our spin quantum number is abbreviated m sub s, and that spin quantum number m sub s is basically giving us a value for that spin. There's only two options. It can either spin plus 1/2 or minus 1/2. Okay? So if plus 1/2 is the one we called clockwise, then minus 1/2 would have to be counterclockwise. Those are the only two options for the spin. Now we can, besides doing electron configuration, which we saw before with the 1s with a superscript 1, that's an electron configuration, we can also give an orbital diagram for its electronic structure. So those are the two ways that we can show where the electrons live. The orbital diagram gives more information than an electron configuration. So it is just another way of showing where the electrons are in the atom, and this is the orbital diagram for hydrogen. What is represented here? Well, the box is representing the orbital, which is a 1s orbital. We see that underneath there. And the arrow that's pointing up is representing the spin of the electron. So if the electron is spinning in one direction, we put an arrow pointing up. If it's spinning in the opposite direction, we put an arrow pointing down. Now typically, well, I'll get to that in just a minute. Okay, so that arrow is just showing the spin of the electron. So I always, though this is just my standard way of doing it, is my up arrow is my positive 1/2 spin, and if you have a down arrow, it would be the negative 1/2 spin. So I'll always use that relationship for the direction of the arrow and the value of m sub s. Now, this is a very, very essential thing that we need to know about electrons. Two electrons in an atom I should say it this way, no two electrons in an atom can have the same 4 quantum numbers. What are those 4 quantum numbers? Well, we have the N, we have the L, we have the N sub L, and now we have the M sub S. Now the way I think about these is these electrons are telling me where the electron exists, okay, where it lives, I'll call it that, all right, and this is telling me what it's doing. All right, it's spinning, and it tells me which way it's spinning. No two electrons can have the exact same 4 quantum numbers. They can have 3 that are the same. As long as the 4th one is different, we'll be okay. So what is the result of that? This is the bottom line. So Pauli exclusion principle has to deal with the quantum numbers. The result of this is that you can have no more than 2 electrons in any orbital, okay? Because all 3 of these numbers together define right down to the orbital it lives in. It lives in the first shell, it's in the S subshell, it's in this orbital, and we can have 1 electron spinning one direction, and we can have 1 electron spinning the other direction. That gives that m sub s a different value. So as long as you have 2 electrons spinning in the opposite direction, they can exist in that orbital. But as soon as you try to put a 3rd one in there, it has to either spin plus 1/2 or it has to spin minus 1/2. And once you have those values, you can't have a 3rd one with those same values. All right, so we can go to the next atom and do the electron configuration and the orbital diagram of helium. Helium is the next element on the periodic table. It has 2 electrons. Okay, so the electron configuration is 1s2. Those 2 electrons are in the 1 shell, the S subshell. They are in the orbital that exists in an S subshell. It can have 2 electrons, and we put at superscript 2 to show that it has 2 electrons in there. And we can draw its orbital diagram. Its orbital diagram would show the orbital with a box, okay? We name the subshell 1s. That's the name of the orbital as well. And now this has 2 electrons, but they're spinning in opposite directions. When we do that, we could then also assign the quantum numbers for each one of those electrons. So each electron will have 4 quantum numbers associated with it. I don't care if that atom has 23 electrons in it. Every electron in it will have a set of quantum numbers that tell where that electron lives and what that electron is doing. So let's give the quantum numbers for these 2 electrons. Where does it live and what is it doing? Oh, no, we're not going to do that yet. We'll do that in a minute. All right? That's what I just said. Each electron has a set of 4 quantum numbers associated with it. The first 3 give its location, where it lives. The fourth one gives its spin, what it's doing. So here's what I was going to do just a minute ago. Here is the orbital diagram, and now let's do the quantum numbers of that, okay? So the first one, what is it telling me? It's in the first shell, okay? So in the distance away from the nucleus, it's the closest one, n equals 1. It is in the s subshell, that's what that 0 tells me. The second 0 tells me which orbital it's in. The third one tells me the spin. Since I used an up arrow, I'm using a spin of +1/2. So we always do it in the order of N, then L, then M sub L, then M sub S. So the other one is in the exact same orbital. So notice the first 3 numbers are exactly the same 3 numbers. N is 1, L is 0, M sub L is 0, but the spin is in the opposite direction, so we give it a -1/2 spin. Every electron in an electron configuration, every electron in an atom will have a set of 4 quantum numbers. First 3 tell you where it lives, the fourth one tells you what it's doing. First 3 tell you shell, subshell, right down to the orbital, and then the spin. All right, so we have got the idea of what an electron configuration is. We've got an orbital diagram. We now know about M sub S. And we know, according to the Pauli exclusion principle, that you can't have more than 2 electrons in an orbital, and when you have 2, they have to spin in the opposite direction.